once again, we get to have fun with functions. Guys never tired. All right, combining functions, composite functions. Say you were going to go buy a car, brand spanking new car. There's different things, that they go and advertise for. Say, for example, that the dealership is being kind and they are having a 5% off across the board. Every single vehicle that they're taking 5% off. And the manufacturer is giving you a $2,000 rebate. How do you want this to be applied? Would you want to have 5,000 or 5% off of the sale price and then take $2,000 off? Or would you like to take $2,000 off and then calculate the percentage off? Which way? You want the $2,000 off, then the percentage? The percentage first, because the percentage of a larger number is going to be bigger, right? So you'd want the percent first and then the discount. Of course, that's the best way for you to do it. What's the best way for the dealership to do it? The other way around, yeah. So when we're putting these things together, we have to make sure that we're taking a look at the whole situation. Another thing is here we got profit. Well, profit, isn't that what's left over after you paid for the materials that you had to make your product? I mean, the cost is going to be whatever it costs you to make the item, correct? So say we were going to go into the, let's see, what should we go into the lefse business? We're going to make lefse like crazy, right? Are there going to be, I knew you'd turn on. Are there going to be costs associated with this? Yes. Now, we sell it for, an extremely attractive retail price. And people are just clamoring because our lefse is so darn good, right? Yeah, I could have said that we were making lutefisk. Lutefisk? You don't know lutefisk? He doesn't know what lutefisk. Oh man. Just take some fish, throw some lye in it, you're fine. There you go. So we've got this, and we sell it, and we're making all kinds of money. Is the money that we make all ours? No, we've got to pay for the cost to make the product. So another way of putting functions together. Okay. So we're going to take a look at what these do now. Fortunately for you, addition, subtraction, multiplication, division work exactly the same way here as they do with regular old numbers. Isn't that just wonderful? So what I'm looking at here then is going to be, sum. We can add functions together. Okay? We can find the difference in functions. Well, difference in functions was just like dealing with how much revenue we pull in minus the cost. That gives us profits, right? Multiplication works the same way. We just multiply them things together. And the quotient, division, works the same way. So when we're dealing with operations of functions, we can go through and use these just like we would expect to. So let's take a look at dealing with these. So I have the following functions, and I want to go through and figure out what they're going to be. Now, f plus g of x. All that means is that I'm going to take the f function, which is what? X cubed. and add that to the g function, which is what? X minus 1. Notice that when I'm doing this, I keep parentheses around each thing. For this, it really doesn't matter because it's just going to end up with x cubed plus x minus 1. Okay? Not a big deal. If I am doing a subtraction, that means that I am going to take x cubed minus x minus 1. Now, if we were to put those parentheses in there, we'd have a little bit of a difficulty with that last part, right? Because what this really means is that I have x cubed minus x plus 1. Yes? Again, make sure we need to follow all the rules. Here, we got multiplication going on, so that's going to be x cubed multiplied by x minus 1. Distributive property gets used, and we end up with x to the fourth minus x cubed. That's it. Last one, where we got division, that means that we have x cubed on top. I suppose I could have means I got x cubed on top, and I have got x minus 1. Is there any canceling I can do? Oh, good. I didn't see any heads, not up and down. I can cancel some x's. It's a good thing. Because you can't. Right? Because if you could, then that means that 6 divided by 2 is 4. So, nothing different here than what you would expect. Okay? So, now it also didn't talk about the domains. Forgot about the domains. Can't forget about the domains. Again, domain is going to be restricted by a number that I put into it that makes it go bad, right? Can I put any number I want in here? And the answer would be yes, so I get all reals. Can I put any number in here that I want? Yes, again, so that would be all reals. Can I put any number in here that I want? Yes, I can, so that would be all reals. Can I put any number in here that I want? And the answer is no. I'm still going to write it out like this. I'm going to say all reals, except x cannot be equal to what number? What would really make things go badly? 1. Because 1 minus 1 is 0, and division by 0 is... Come on, you're supposed to, with gusto, say this all at the same time. Division by 0 is... Gotta say it with gusto. Division by 0 is... Division by 0 is? Thank you. Anything to the 0 power is? No, 1. Anything to the 0 power is 1. These are 2 things that you got to make sure you keep in your minds. Okay. It's terrible, 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 terrible. Okay. Demand for a certain electronic component is given by that. Producing and selling the component involves a monthly fixed cost of $1,999 and a production cost of $4 for each component. Okay? So, write an equation that models the total revenue. Well, we got this. That's going to be our demand, right? That's how much people want, right? So would demand be like what we sell? So if we have used this formula and we have determined that there is this much demand for our left side, is that what I would use to make my lefts on a daily basis? I mean, after all, who wants leftover lefts laying around, right? You ever think about that? You go over to say, oh, let's use Hugo's for instance. they go and have those wonderful chickens sitting there, right? Rotisserie chickens that they've got. Do they want to make enough rotisserie chickens so that they can sell them? Do you want people walking in there and looking at that and going, "Oh, no chicken"? Is that a good thing? No, because eventually they come in there at a specific time of the day when they're going to get chicken, and they're getting, "Oh, no chicken." It's going to make them go someplace else, right? Just so that they can get their chicken. Now, do you want Hugos want a situation such that when their workers get off work at night, so say we have two of our young people working there till 10 o'clock at night, and they're handing you chickens on the way out because they don't want to waste it. Would that be a useful thing? No, that wouldn't be a good idea. One, some people don't like chicken. Two, who wants to take a chicken home every day, right? But they can't give, yeah, I'm sure you agree. Yeah, it's good stuff. But do you want to go and do something like that? Do you want to make too much product that you cannot sell? I don't know, back in the day, if you'd have had to have been awfully young, but every once in a while they'll show a picture, or they used to show a picture of the old Ford plant down in St. Paul where they made the Ranger pickups. And they'd have a picture of it, aerial view. And the parking lot was just simply, or their back lot was simply full of these pickups. Is that a good thing? No, it depends. Should an auto manufacturer make sure that they can make just enough product? So they got a formula based on that to determine for that product. And if it's going to cost you $4 for each component, you'll notice that they go and take that and multiply it by what? X number of components, right? But as we go through and we look at this, we see that it turns out to be 4x. So it gets put into there. Right? We're just putting things together. Unconventional vehicle sales. I didn't know that my hybrid was a unconventional vehicle. Okay. Does this data show a combination of functions? If I want to talk about total vehicle sales in the United States, do I have to take into account E85, diesel, the hybrids, and the plug-in all electric? Do I have to put all those together? Do we sell as many of each category? Obviously, the E85s are better, get sold more, but is the E85 easier to make? Probably, because you really don't have to do anything except a few adjustments in the fuel injection system. Diesels have been around for a long time, but does everybody want to drive a diesel? Pickup, maybe, but a little car? No, it's not doing anything. I mean, could you imagine Rental Guard's smart car as a diesel? Although Volkswagen did make a diesel Rabbit back in the day, and those things basically lasted forever. So functions, things are being put together. So it says, let's see, shows that. The question is here, the functions that go and determine that. So add the functions together. Can I go and take the F and D, the flex fuel and diesels, can I add those together and come up with a number of vehicles? Yeah. Could have I done that up here? I would have just taken the numbers off that I see how many vehicles sold if I knew what those exact values were. Not a big deal. Let's see. Average cost. Okay. If you've got a company and you're making something, let's go back to our left side. Right. So, what's one of the most wonderful components in left that we have to have? Otherwise, it just doesn't work. Sugar. Potatoes. So we got sugar, we got potatoes. Let's pick on potatoes, even though both of them are produced around this neck of the woods. Are potato prices cheaper after harvest? Got lots of potatoes we're sitting around, don't we? What about prior to harvest? Would we want to be buying potatoes then when there's not as many potatoes there? We have scarcity going on? Same thing with sugar, although sugar is a little bit less volatile. When you take a look at a product that fluctuates in price all the time, by the way, let's try this one on for size. What happens if our Alexa was a delivery service? We're delivering Alexa. Is the cost always going to be the same? No, because we're delivering our Alexa, and what's gas price right now? $2.29. Before Christmas, it was $2.19. We can even find it maybe cheaper in a few places. Is that going to affect what our cost is? Yes. So if we were doing the delivery service idea and we wanted to take a look at our average cost per unit per year, well, wouldn't that have to take into account all the fluctuating gas prices all the way through? I'd want an average gas price that I paid. That would help us. So, it says Sunny's greenhouse produces roses and the total cost for the production of X hundred roses is right there. So it's $500 always, and 50 times X hundred roses. So, if I wanted to go and find the average for this, I would have to divide by what? I would have to divide by X, because that's the number of roses, right? Okay. So if I take a look at that cost, here it is. I assume that you've heard the idea that the more we have, the cheaper it gets. Buy in bulk. I mean, after all, you go down to Sam's Club and buy your Lefsa in bulk. You get huge, big bags of Lefsa and you just come home, right? That is if they've actually sold it. Is that a good way of doing things? Not necessarily. There have been studies done that buying in bulk for the average person doesn't necessarily work for everything. Certain things it does, but not everything. Now, one thing that I want to get to here is this. Composition of a function. I want you to make sure that you have it written down, and what you have written down is right in here. This is the important part that I'm going to be using. Part of the reason for this is having things written out in composition notation is not as easy to understand as it is in function notation. Function notation kind of leads us to this idea that, hey, we can take what's on the inside and work our way out, which is what we need to be thinking about. So, I'm going to show you this in action. There are two machines in a room. One machine squeezes oranges to make orange juice. The other one is a canning machine that puts the orange juice into the can. Thinking of these two processes, we got the squeezing function, which is D, canning function is F. So, if I talk about this idea, I want to do F composed with G. Okay? That means that I take F of G of an orange. What does this mean? This means I take the orange, I put it into the G function first. So if I take the orange, put it into the G function first, is that a good thing? Because it's going to do what to the orange? Squeeze it. Okay? And once I squeeze an orange, what do I get out? Juice, we hope. So I squeeze the orange, got the juice, then I take the juice and put it in the can. Does that make sense to do? What about B? Does that make sense? Does it make sense for me to take the orange, put it into the F function, take that out, and then put it into the squeezing function, right? So I'm supposed to take the orange, put it into the can, so the orange is in the can, and then I'm supposed to go squeeze it? Would that make sense to do? No, but that's the order of what's going on here. So which function makes sense? Well, the only function that makes sense here is f of g of orange, right? Because g goes in the squeezing machine and then it goes into the canning machine. So let's take a look at how this goes. We're going to find the following compositions of functions based on this. Now, this looks ugly, but it really isn't all that bad. Now, like I said before, I try to use this as function notation like this because it just makes a lot more sense setting it up, and I'll show you why. H of f of x, okay? This is going to be equal to h of whatever's on the inside. What is f of x? Okay, f of x is 2x minus 5. Okay, now I've identified what the f of x function is, and now I'm supposed to put that into which function? The h function. So it's just like doing a substitution. This is now going to be 1 over 2x minus 5. Okay. What's the domain? Well, the domain is always going to be what works in these functions. What doesn't work here? Well, x can't be 0 there, can it? In the h function. If I look at this one, what can't be used now? Is there a number that x cannot be? What could be 2.5? If I were to take 2 times 2.5, I get what? 5. 5 minus 5 is 0, and division by 0 is 5. It gets better. Okay? So, I can't have 2.5. Easy enough. Let's try the next one. So I got f of g of x. So I got f of g of x. What is that equal to? F of. What's g of x? Okay, so I got 6 minus x squared. Okay, so now that gets put into what function? The f function. So now, wherever I see the x, I'm going to replace it with the 6 minus that. So that means it's going to be 2 times, and then I put it in as 6 minus x squared minus 5. So I work this out, and it looks like I'm going to end up with 12 minus 2x squared minus 5, and I end up with negative 2x squared, and that's going to be plus 7. Okay? Is there anything I cannot use in that function? Nope. This is going to be all reals. Okay. That works, right? So, there's this red one here. Let's do this one. I've got g of f of x. G of. Okay? Well, what's f of x? 2x minus 5. And that's got to get put into which function? G function. So that means it's going to be 6 minus parentheses 2x minus 5 squared. So that means I'm going to have to do some FOILing there, yes? So that means that it's going to end up being 6 minus parenthesis. Let's see, that's going to be 4x squared. 5 times 2 is 10, so that's going to be negative 20x plus 25. Yes? So nice little trick is whenever you've got that, you take that times that and then double it. So 2 times 5 is 10, double it, 20. You got two of them. So that means that I end up with 6 minus 4x squared plus 20x minus 25. So when I'm all done, negative 4x squared plus 20x minus 19. So, is there something I cannot put in there? No. So it's all reals. Does it seem relatively easy to deal with? Just a lot of simple manipulation. Not bad at all. So, let's see what else we got. So do that. Now, you can put these in. I haven't played with this as much with the graphing calculator. So I don't necessarily do quite a bit of this, but it'll work. So here we go. What we are going to do is this stuff here. Let's see here. Well, I'll have to figure. Okay, y is equal to. So, first one. Second, square root of x minus 5, closing. Next one down here is going to be 2x squared minus 4. Now, I do believe this. Oh, where? How do I do that again? Can't remember where. Ah. Yep, there it is. Okay, where these things are hiding at is vars for variables, y vars because we want the y variables, and we're talking about functions that we've created, so they are sitting there in the functions. And so now I'm going to put in 2, which is y2. So what this will do is it'll take what's in y1 and it'll take what is in y2 and it will graph them. So if I hit graph, let's see, and I want it on this was supposed to be on a window of negative 1 to 10 by 0, I said 10, go down, 0 to 200. Right. So, if we were to go and run through the trace on this, got that one, got that one, got that one, y3. We don't see y3, do we? I had to put the right in the window in there, didn't I? You guys getting the same thing? That's odd. Well, if we go and take a look at the table here, you'll notice I see what's going on here with this. On Y1, we get error, we get error, we get error, we get error. Because you got to remember, you can't do the square root of a negative number, so that's why it shouldn't be there. Evidently, the software that we've got these things doesn't. Maybe some of you got the newer software out there and actually showed the gap in there. So, this really couldn't kick in until we managed to get over here to 5. So when it was asking here for your domain, the domain would have to be greater than 5. That is the first place it's going to kick in. And if you don't believe me, it goes over here, Y3 error. So, I suppose, left that in there like that. Y equals try something one through real quick. Okay. That does that. That's kind of cool. Learn something new every day. Okay, what I did, guys, was I went over it, and if you arrow key over here, you can go and change what this is. So that one gave me a 0 and a line. Hit enter, gives me a 0. That's what I should have left it at. And so it's just going to trace where it was, but it will actually draw the line here on 3. So that's when I hit the graph on there. It goes through there, shows you where that one should be. Shows you where that one. See, even I learned new things on this stuff. Get that, and then you get the line. Kind of cool. All right. So now, what happens if they go back here and they want us to go and do the f over g? Well, we go back to y equals. So we can go and change this here from addition to division. Okay. Change our window. What do they want us to do this on? From 5 to 15. And they want us to use this on from 0 to 0.016. And I hit graph. Let's see what we get. Don't see much there. Don't see much there. Let's see what it's supposed to look like here. Okay. Still thinking. Still thinking. Ah, look at that. So there we go. So what other one do they want here? Do they want F composed? Okay. So they want us to compute fog. F of G of 3. I don't think. Yep, they do. Okay. So this is why I was talking about this idea of having the notation as F of G of X. What we can do is we can put one into the other. So if I want f of g of x, that is going to be f of, well, what's g of x? Well, that's going to be the 2x squared minus 4 bit, right? and then this goes into the square root of whatever that is, 2x squared minus 4 minus 5. Now, do we really want to go through and try and figure out all that mess? Not necessarily. We can cheat a little bit on this. So what we can do is get this right. According to what this says, should be y of that of that. Let's see if I can't graph it out like that. Parenthesis, y2, close it, and don't think this is necessarily going to work. It might work. Nope, not going to work. That one. And I don't know. So we'll give it a try. Give me a fail here real quick. I'm going to leave it like this and see what it does. It might just go through and multiply. So I'm afraid it's going to do. We'll have to look at the composition of functions and how it goes through there. Played with it in the past. Yep. Okay. I wonder if it works on a regular screen like that. Let's try it here once. See if I can't replicate what they've got there. I got that function, parenthesis, bars, go there, go to, no. Two, parenthesis, -3, close it. Huh, good. Don't know why. Ooh. Maybe I was right to begin with. Probably would help if I change my window too. Because what's happening here is we're taking one number and putting it in. I'm going to go to second table. And let's see, we got our numbers here, like that, like that. Big numbers, small numbers, so let's go here. We'll go from 0 to 5, or 0 to 10. Let's see, maximum, I'm going to put that up at, say, 50. Graph, see what it does. Oh, there's one little circle. Doing that. Doing that. And there's the graph piece. Now, what's happening here is we want to put -3 into y2, get an answer, take that answer, put it into y1. It's kind of like the orange in the can again. So if I hit the trace, and now what I'm going to end up having to do is redo this all over again because I wasn't paying attention to what I was doing. -5. And I got to go negative. I forgot I'm going to have that negative in there for that. So if I put in -3 to the function, it should come back where that's coming from. It goes down, comes back up. It's kind of cool. And there we go. The composition of the function's coming in there. So if I go and hit trace, and I put in -3, it's going to return a value of, oops, helps if I'm on the right one. There it goes, -3. And I get 3. Technology is wonderful stuff. But the idea is you plug the number into one function, get an answer, plug it into the next one. So, and there you go.